Today we're going to be talking about convergence. Recall that sequence of numbers an and r is said to converge to some limit L in R if for all epsilon greater than 0 there exists an n in the natural numbers such that the distance between an and L is less than epsilon for all n greater than or equal to n. Okay? So what this definition says is that I look at the indices of my sequence, and if I can find an index far out enough such that the elements of the sequence beyond that index are all within a distance of epsilon from my limit point L, this means that my sequence stays within a neighborhood, an epsilon neighborhood of L. So it approximates L to the error epsilon as long as we're past this index. But since the error is arbitrarily small, then we conclude that the sequence actually somehow represents L in its limit. Okay, so geometrically speaking, I have the number line, and I have my limit point L, and I have my sequence of points. Then let's say this is A1, A2, A3. Here's A4, A5. Maybe the sequence jumps out here for A6, and then A7, A8, A9, and then eventually it gets pretty close to L. Well, once I've specified an epsilon, let's suppose that I specified this epsilon, okay, this distance epsilon, okay? So then everything, as long as I am past an index of 8 in my sequence, I stay within this epsilon neighborhood of L, okay? So for this value of epsilon, I would choose capital N, in this case, to be 8, and then everything beyond 8, the sequence is trapped within this epsilon ball of L. But remember that epsilon is arbitrarily small, so I could keep shrinking this ball, and for every one of these balls, the sequence will eventually become trapped within the ball. Another way of saying this is that for every one of these epsilon neighborhoods of L, no matter how small, infinitely, or like the full tail of the sequence belongs to that epsilon neighborhood. Only finitely many elements of the sequence are outside of that epsilon neighborhood. Okay? So if I were to choose an even smaller neighborhood of L, if my limit point of the sequence was truly L, then only finitely many members of my sequence would be outside of this epsilon neighborhood. Okay? Now, another intuitive reason for this definition is if we look at a sequence of rational numbers such as 3, 3.1, 3.14, 3.1415, etc., then we could say, well, these are just the first n digits of the decimal expansion of pi. And so in the limit, this is actually going to approach pi, okay? But notice that each of these are rational numbers, okay? So each of these, this is 3 1/10, so 31/10. This is 3/1. This is 314/100, etc. So each element in this sequence is a rational number, but the limit point of the sequence is irrational. Namely, pi cannot be written as a fraction. So what this tells us is that the notion of limit points of sequences actually allow us to pass from the rational numbers to the real numbers by approximating any infinite decimal expansion number with the first n digits of the decimal expansion. Okay. All right. So let's talk about sequences of functions. Okay. So if I have let's suppose that now I have a sequence Fn of functions. These functions are, let's say, functions from the real line here itself. Okay. then I can denote that I kind of have a sequence of, let's say, some functions. So maybe I have a sequence of functions that looks like this or something. Okay. Or maybe let me try a better sequence of functions. Perhaps I have a sequence f1 like this. Here's the graph of f1. Here's the graph of f2. And I can just graph all the functions in the sequence, okay? F3, etc. Okay, so if I have a sequence of functions, then I can define pointwise convergence just using this definition. Okay, so if I have a sequence of functions, I can look at the value of those functions at any point x on the real line, and then just ask the question, does the sequence converge at that point? And if it converges at every point, then I'll say that this converges to a function f pointwise. Okay. It turns out that this is actually not the only way to define convergence of functions. Obviously, this is a lot of data, a lot more data than just a sequence of numbers. This is a whole sequence of functions. And so there's many different ways in which this function can geometrically or intuitively be said to converge to the function f. And this is just one of those ways. And so, in going back to our previous example, something would look like this, then we would say, if my sequence of functions, let's say this was f1 in pink, then f2 is in green, and f3 is in orange, then intuitively speaking, this function would somehow converge to pointwise to a function that looked like this, everywhere except for this singular point, and then at this singular point, let's say x naught, it actually wouldn't be convergent. Actually, no, it would be convergent. It would converge to this point 1/2 here. Yeah, because all these functions are going to the point 1/2. So this is what this sequence of functions would converge to pointwise. Okay, and so if the pointwise limit, you just take a horizontal or vertical slice, and then only consider the sequence on that vertical slice, and look at where that converges. Okay.